All right, let's take a look. We've done some background about matter purity. Our first chapter talks about the atmosphere in regards to ozone and ultraviolet protection. It's going to bring up a few things that we haven't talked about. We mentioned energy in the first day, but we need to talk about the electromagnetic spectrum and the different types of energy and how different types of energy interact differently with matter. It then is going to bring up amount, and we can measure amounts in a number of different ways. There's a convenient way to measure amounts in gases. It's called mole fraction. And so we'll spend a little bit of time on that. It also talks about the different regions of the atmosphere and ozone's protective ability. We'll read that out. Just mentioned the very first part in talking about the atmosphere is it says the atmosphere can be divided into multiple parts, but it only tells us what two of them are. So we've previously established that the atmosphere is a mixture of gases and that it is mainly dinitrogen and dioxygen, using the full chemical name for nitrogen and oxygen. Because in terms of environmental issues, it's beginning to settle, we're beginning to get a sense of what our physical project for this term is going to be. We're going to measure some water quality. The city of Austin wants to know how much nitrogen is in the water. Well, they don't mean this. They mean nitrogen that is combined with other things. They specifically want to talk about nitrates. So, to say nitrogen becomes ambiguous in the environmental realm, okay? So this is dinitrogen and dioxygen, di meaning two, and that removes the ambiguity. When we say, oh yeah, hemoglobin interacts with oxygen, what we're really telling you is hemoglobin interacts with dioxygen. It picks up the gas. And there is no metabolism for dinitrogen, not amongst mammals. The only thing that has a metabolism for dinitrogen, does anybody know?
Bacteria?
Yeah, it turns out that it's incredibly environmentally important that there are nitrogen-fixing bacteria that live, I'm not going to say the word parasitic, just said it out loud. They're symbiotic with plants, but not all plants. And they live in little nodules on the roots of some plants. And they feed off the plants. They take nutrients, they take sugar. And in return, they turn nitrogen from the atmosphere in like little pockets in the soil into ammonia, which acts as fertilizer. So the plant grows better and gives the bacteria more nutrients.
Tomatoes, I think they like. Is it tomatoes?
It's mostly non-useful, not crops.
Is it
So-
orchids? It's a specific plant.
Clover.
Really, oh, okay.
And some legumes. You know what a legume is? It's completely unimportant if you don't. Yeah.
Peanut isn't it?
I got my PhD in the nitrogen fixation lab at the University of Sussex, and 50 years ago, they said we were 5 years away. 40 years ago, they said we were 5 years away. 30 years ago, they said we were 5 years away. I don't know how many years away we are now of transferring, either capturing the biology's way of doing this low energy, turning nitrogen into ammonia fertilizer, or adapting the genes in plants so that they accept the bacteria and adapting the bacteria to live on plants that they currently don't live on. When that happens, that's Nobel Prize material. That's plants will now grow in places where they didn't grow. They may also strip the minerals out of the soil because they're growing where they're not supposed to grow. Every good thing comes with it's tinged. Okay, so the gas is a mixture. We know what a mixture is. Stuff's acting independently of each other. All right. And the atmosphere has regions. Our book only gives us 2 regions, and basically the regions in the atmosphere are dictated by altitude, how far away you are from the planet's surface. And actually our book does this in kilometers. That's the, what is it? It's about 10.
Oh, I got
I
it.
just
It's
looked
10
at
to
it.
35. Or
Yeah, it's a little bit over 10. Here we go, 10 kilometers. Or this is where all the weather happens. This part right here is the troposphere. And I'm sure if you went and did meteorology, you would subdivide this by, oh, my clouds are at this height. And then once planes fly at a particular altitude, I only know it in feet. I can't say it in meters, although we could probably figure that out. Planes travel about, what, 35,000 feet? They're about 3 feet in the meter. 10 and change thousand meters. Yeah. And then above that, we have the stratosphere. And the stratosphere goes to about 50. We watched the Blue Horizon launch today. They shot people up into space for a total duration of
8.5 minutes.
8.5 minutes. They spend a couple of minutes getting to space, they spend a minute in space, and then they come back down again. And it's set on the side of the screen how high they went in kilometers. How high did they get?
God, when I looked at that, I only saw it at like 5 kilometers at one point, and then I stopped looking at it. So.
I think they went like 100 kilometers up.
Yeah. Paige will probably remember exactly.
Okay, so this gets to be the stratosphere. And then there's other stuff. And then ultimately you exceed the gravitational pull of the planet. And it's the gravitational pull that's keeping the mass in each of these particles. Nitrogen atom has an atomic mass of 14 atomic mass units, 14 grams per mole. And we have 2 of them, so this weighs 28 Daltons, atomic mass units, grams per mole. And this weighs 32, so they're light. But they're still pulled to the planet's surface. And think about all of the gas particles, mostly, more here than there. All of these are being pulled down to the planet's surface. What physical phenomenon does that give us?
Gravity? What?
So the gravity is acting on each and every individual piece of matter that has mass and is pulling it down to the big piece of mass, which is the center of the planet. So all of that weight, this is you. You're right there. The weight of the untold millions of atoms of gas directly above your head is pushing down on you. What does that give us?
Oh, yeah.
That's where pressure comes from. Okay. So we have gravity. The gases are very light. They're very small. There's big spaces between them. They're moving around rapidly. And the planet is pulling them to the surface. So they have motion, but the planet is pulling them down. So when you're close to the planet's surface, there's more available gas here. And as you go to higher and higher altitudes, humans aren't going any higher than this. Here's a mountain. There are mountains on the planet where you really either cannot or should not go without the medical assistance of external oxygen, because as you go away from the planet, you feel less and less pressure, and you need the pressure so that the hemoglobin in your bloodstream, which isn't particularly efficient, has enough pressure to fill up with oxygen. Okay? There's other stuff up here. There are words you'll have heard of, ionosphere and stuff like that. It's not in our book. It's not in it. Now, in the stratosphere itself, somewhere between about 20 and 30 kilometers up, this is where we see most of the ozone showing up. Sufficiently enough that we call it a layer. There's an ozone layer. We're going to find out, well, we don't even know what ozone is yet, but we're going to find out that up there, really good. Down here, really bad. So we want lots of ozone, but we want it up there. We do not want any ozone, or as little as possible, down here on the surface. It's detrimental to materials. So it degrades things that we take for granted, plastics and such. But it also deteriorates people. It's a very unstable molecule, and it does something sensationally important because of its instability up here. Okay? There's a little diagram on page 4, and it just says troposphere, stratosphere. Here is the peak
I thought this was, that graph was really cool.
of where the ozone is. And then also, there's a diagram about temperature. And there's a couple of things that we know. That the temperature of the planet's surface is warmer than as you go up in altitude. If we lived in a state that had mountains in it, the temperature is always warmer at the base of the mountain than it is as you go up. So temperature drops, but then it spikes again. It goes up again, and it's a little bit offset, but it is kind of coincidental. I'll hold it up for people watching at home. So we have two diagrams on this page. This first diagram here shows the concentration of ozone as you increase altitude, and it definitely spikes right about here. And then this diagram talks about temperature. And the highest temperatures on the planet's surface, as you go up, that temperature decreases. And then as you continue to go to the very upper atmosphere, high energy events are happening here. We are exposed to cosmic radiation, which contains X-rays and gamma rays, and those high energy rays are causing this heat, okay? And then eventually it comes back down to, oh, there's no atmosphere anymore because you've exceeded the gravitational pull of the planet, okay? Yeah.
What happens to the top of the ozone layer?
So, this is the part that we interact with, okay? We've got climate, we've got all of our resources. This is where we are, where we live. So we're mostly concerned with what's here, but we have to be concerned about other things that we didn't previously think about, because they have an impact on what happens here. The sun gives out all forms of radiation. Radiation in the form of electromagnetic radiation. The electromagnetic radiation from the sun is what we call a continuum. It is one of absolutely everything. Could have done that a little bit better. Some waves are very long. Some waves are very short. And when we describe the electromagnetic spectrum, they usually just show it as a band, because it takes a complex three-dimensional thing and just puts it all in a chart, all as a scale. We put the long waves here. These ones are low energy, and these ones are high energy. This is the answer to your question. We will get there. You know, it's content from this chapter, but this is what we're getting to. Okay. So the really long waves turn out to be things like radio. If you want to know something about stars, you can look at them with a telescope. But stars give out all forms of energy, which means you could listen to them as well. And there are radio telescopes. They look just like giant satellite dishes. I mean, giant. There's a couple of big famous ones. There's one at the start of that James Bond movie at Arecibo in...
South, right?
It's not in Chile. Is that in Chile?
Yeah. It's
Or is it
almost
in...
Argentina or Chile.
Okay. It's in South America.
It's the most southern point of South America, like or near the
No.
most southern point or whatever.
No, it's more tropical than that. Anyway, they found a big, there's a big valley, and they said this would be a great place to put a dish. And so they just made a massive dish in a valley, and it's huge. A James Bond movie starts with, is it Die Another Day? No,
No, it's
No.
007 GoldenEye.
it's GoldenEye.
GoldenEye. It's a game. It was from Nintendo.
Oh, you played the N64 game. It's better than the movie. Other things that we can listen for: microwaves, and then infrared. Infrared is the energy that we associate with heat. So when we feel the warmth of the sun, we're experiencing this. Then there is a very, excuse me, very narrow band that is visible light. And the visible spectrum goes red, orange, yellow, green, blue, indigo, and violet. And then above violet, we have ultraviolet, and above ultraviolet, we have X-rays. And then above X-rays, we have gamma rays. The long waves that are low in energy are also low frequency waves. Frequency is, if I picked a spot in space and I counted for 1 second, how many waves are going to go past that spot? I put my finger here, and this one that's got really tight, it's got lots and lots of information in it. In 1 second, lots of those peaks go past my finger. So this is a high frequency wave. This one, if I put my finger in the space and I count to 1 second, oh, only one wave managed to get past my finger in 1 second. So this is a low frequency when it's long wavelength. The high energy waves are the high frequency waves. Okay. Now, it turns out that the way that nature has set itself up is that energy interacts with matter in a different way with each type of energy. Radio waves make electrons tumble and spin. Microwaves make whole molecules tumble and spin. And that, making things move, turns out, well, that's kinetic energy. That, we associate that with heat. This, infrared, makes individual bonds inside a molecule vibrate up and down as a stretch or side to side as a bend. Visible promotes low energy electrons from one position inside a molecule to another position inside the molecule at a low energy interval. Ultraviolet does it more violently. It can take an electron and boot it to a high energy. It can take an electron and knock it off the atom altogether, which means everything here is now dangerous. These are ionizing radiations. X-rays knocks electrons clean out of matter, knocks them out. And then gamma rays are now so tight, the wave for them, the frequency of this wave, the wave length of this wave is so tight. These are that's the first type of energy that can actually see the nucleus of the atom. If this is the size of an atom, right there, a radio wave comes along and completely misses it. Visible light misses it. X-rays wing it. Gamma rays, they can hit that atom and do something damaging to the nucleus. They can do real high energy events right here. So anything on this side of the electromagnetic spectrum, the sun, our friend, is emitting is something that we don't want down here. We don't want that. And by miracle, our planet has a handful of safety devices that prevent those energies getting to us. Okay. First off, here's the planet. The planet is magnetic. We have a north and south pole. We have, why do we have magnetic poles?
Rotation of the Earth?
Okay. Well, it rotates
Well,
more or less on its pole.
well, it's part of their core, right? It
Ah.
has something to do with their core, the metal
Yeah.
core, right?
Deep, deep, deep at the center of the planet, there's a big blob of molten iron. And what do we know about the iron that we dig out of the ground? Iron is Fe. Iron's magnetic. So we have a giant magnet at the center of this planet. And it has these magnetic lines of force. Okay. Magnetism, these are electromagnetic rays. Magnetism interacts with all of them, but it interacts differently with different types. First thing, when the high energy waves from the sun hit the magnetic field, they get displaced, they get bent, they get knocked out of the way. The low energy waves manage to get through. So we get heat and visible light from the sun. We get the microwave and the radio as well, but we can't hear microwave and we can't hear radio. We can use it for communications, but then turn that into the audible range at the end. So the low energy waves get through. So if I'm on the planet's surface, I don't have to worry about what's called cosmic radiation. These two. I mean, technically it counts as ultraviolet as well, but these are cosmic rays, the gamma rays and the X-rays. Very, very high energy, deleterious, dangerous waves. Okay? Now, ultraviolet is at the low end of dangerous. So, this is my ultraviolet ray and it gets through. On Tuesday, we talked about one of the world's first mass extinctions. And it happened when photosynthesis happened, probably on the surface of a body of water, put a byproduct, oxygen, into the atmosphere. The early atmosphere did not have oxygen in the atmosphere. These rays come straight through. There's one of the online low-level introductory classes that we do. We talk about, there's an experiment that a guy called Miller did, where he took a great big glass vessel and he threw some water in there, and he threw in what he thought was the early atmosphere, some methane, maybe some ammonia, and then he sealed it. He put 2 electrodes in there for some lightning. And spark, 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 spark. And then you open it up about a month later and you find out that there are very small molecules have been made that we've turned methane and ammonia into like glycine, which is an amino acid. So that's one of the building blocks of life. Okay, so the pathway to make these small molecules existed, but what his experiment didn't include was, in the early days of the Earth, there was nothing to protect us from the sun. That the ultraviolet was coming in. And we're going to learn that ultraviolet is like a catalyst. It's a kick up the backside. It's an energy jolt that's going to make some reactions that were previously impossible. It's going to make them possible. And it makes reactions that happen in the absence, it gives them products that wouldn't be possible otherwise. One of those is going to be ozone. So, the ultraviolet is beaming down on primitive planet Earth, and then at the first sign, there's a little clover, look, at the first sign of green life, it was probably algae, that puts oxygen into the atmosphere. This moderately high energy, ionizing energy, hits oxygen and converts it into ozone. Ozone is a form of oxygen. It's what we call an allotrope. Allotropes are forms of an element that occur in different types. It's just a different type of form of the element. Oxygen exists naturally as 2 oxygen atoms stuck together, but it could also exist as 3 oxygen atoms stuck together. And at some point, we're going to want to look to see what that molecule looks like, and it's not going to be a happy experience, because this is a very, very odd molecule. So odd that you'll scratch your head and say, from what I learned in chemistry, this molecule shouldn't exist. It doesn't look stable. It doesn't behave the way that I'm expecting things to do. It doesn't do the octet rule. It just doesn't do what it's supposed to do. So it turned out to be a little bit odd. Well, that ozone collects in a layer. Just enough of it. And it does the most fantastic thing, is that oxygen plus ultraviolet light makes ozone, and then ozone plus ultraviolet light absorbs more ultraviolet light, and it blocks the UV from coming in. So once oxygen had made it into the Earth's atmosphere, ultraviolet zapped it. That's the actual, we've decided it's a word. We've decided that a high energy event that happens because of cosmic radiation is called a zap. Zaps it to be ozone. Now the ozone sits here, and the ultraviolet, which is my red wave, doesn't make it through anymore. I just wiped out a civilization. There was people here.
Was it North Pole and Arctic circles?
So, your question. The question is, what happens above the ozone layer? Things that are different than that's below it. That ultraviolet roams freely here. It is absorbed by this layer, and that there is ozone up here and there is ozone down there, but it kind of peaks at this 20 kilometer range right here. There is not much as you go higher and higher. The amount of gas molecules get to be more sparse, less of them, but we're going to have higher energy radiation.
In a bad way or?
Not in a good way. Not in a good way. So we saw the guys, so there was a launch, we watched it today, Blue Horizons went into space for 2 minutes, right? They went in their oddly shaped vehicle out here. We think they were 100 kilometers up. The little diagram on the screen said 0 gravity.
Mm-hmm.
So they went to the very, very edge of the Earth's gravity, and then they were, but not beyond it, because they came back. Okay. Here, you're in a direct line of sight from all of the rays that the sun gives you. So when you finally make it up to here, where the space station is, that's my space station. We just retired an astronaut today, this morning, Sunita, whatever her last name is. She'd been in space 602 days.
What was the longest anyone had been in space, right? There's someone just came
well,
back recently, I think.
I'm not entirely certain, because it might have said it was the longest a woman had ever been in
Okay, there you go.
space,
That could've been it.
because we had, whatever.
Gotta get specific.
But yeah, I think some of the Russian cosmonauts were up for a while. 600 days is a really long time to spend in space. A lot of that was unintended, because they were stuck.
Or did he get paid?
Right.
No. That's.
They get paid overtime. Yeah.
Oh, okay, I
I
was like,
don't
if they don't get paid.
I don't know.
I read that they weren't gonna get paid for overtime.
Yeah, I have no idea. I have no
300
idea.
days of overtime.
Yeah, they got stuck,
Or 600.
and a rescue mission had to go and get them.
If you're physiologically, there's like lasting things you have to deal with.
So yeah, there's muscle mass that you lose. There's probably bone density that you lose. It's the same as working in a submarine. You never see anything in a long focal distance, so you kind of just get cramped. Your physiology changes. But the single most important thing is they've had a lifetime of X-rays. You go to space for a handful of days. That's it. You've had all the X-rays you're ever going to need your entire life. It becomes dangerous, and we can't make spacecraft out of lead. Lead shields radiation, but it's also incredibly heavy, and we need the vehicles to be light so that we can launch them. Yeah. So stuff that happens up here is a higher energy chemistry and physics is happening up here, which is why temperature is big here, and then as you go away from the planet, temperature goes down. There's less stuff. The atoms aren't as close to each other as they were before. They're not colliding with each other. And then it goes back up again because I've got my high energy stuff happening.
What height would you go skydiving?
It was like
Ooh.
10,000. I did it. It was.
What height did Felix Baumgartner jump out of that? Oh, did you see that guy? So he went
A
up
couple
in
years ago?
Yeah, he went up in a balloon,
Oh, that's right.
and he had to wear a spacesuit. And he went to as far as it was safe, that there was still gravity.
Yeah,
Because you can't skydive from the International Space Station.
Whoa, you just flip out or.
Well, what happens is, yes, you do, there is a gravitational pull, but there's also the orbit. And when you try to skydive from here, you actually just stay in orbit. Yeah, that's not good.
It's 10 to 14,000 feet. For
So
skydiving.
regular skydiving is in 10,000 feet, which is 3,000 kilometers. Still high. But planes are at 30,000 feet, which is
11,000 and some change.
that's meters.
Yeah.
Oh no, we were so wrong. Planes are at, say that out loud. How many meters?
11,666 meters.
So a little bit over a kilometer.
Yep.
And where do skydivers go?
At 10,000 feet. So
10,000 feet. What's that in meters?
Oops. That's not the number I wanted. 3,333. So
Not even half of a kilometer. That's a parachute.
Would it be possible to go skydiving?
Well, find out how high up did Felix Baumgartner go? Felix, B-A-U-M-G-A.
you pulled up right away.
It's because your phone's listening to you.
38,900 meters. So 320, right?
Like right below the layer?
I've never seen him interviewed. He must just have ice in his veins.
What would happen if he went a little bit higher?
He would float free of the Earth's
Like just
downward gravitational pull and would be subject to the translational motion as well, and he would go in orbit
That's crazy. So
and
because
eventually.
ozone is like up to 30. Ozone is 15 to 35
Yeah.
kilometers up. So he literally went up.
Okay, he
He went up 2,000 meters up past that then.
Okay. Okay, so ozone has been mentioned. We've said what it is. We're not ready to talk about it. In order to talk about it, we have to go back to Lewis structures, stuff like that. There's a couple of other things that our book says we should probably talk about first. About the beneficial end. So right now, what we've said is that everything that is a higher energy wave than visible is potentially dangerous. It is high enough in energy that it can move, it can promote or dislodge electrons from matter itself. Remember, matter is atoms. At the atom center, there is a proton, or multiple protons and neutrons, and on the outside, there's electrons. So be removing electrons from the outside of matter itself. The number of protons now exceeds the number of electrons. The number of positive things exceeds the number of negative things. We're going to make positive materials. They're called ions, and so this is ionizing radiation. Specifically, so let's write a couple of facts down and then go investigate how much more is available to us. Ozone blocks solar ultraviolet light. Ultraviolet light itself is subdivided into categories, and depending on who you read, some of those subcategories also have nuance to them. So our book says X-rays, ultraviolet, visible, infrared, and it gives wavelengths. And it's going to subdivide the ultraviolet band on the electromagnetic spectrum into three types. They are UVA, UVB, and UVC. Which way does our book do it? With the full letter? Okay. So it's possible, I'm going to write it the way that our book does it, to go A, B, C, but let's speak in the same language as the book. It calls them UVA, UVB, and UVC. Okay. This symbol, the little squiggle, means about 200 nanometers. We're probably going to have to remind ourselves what that means. And then 280 and 320. So centered at about 280 nanometers and about 320 nanometers. These are nanometers. All right. Well, I know what a meter is. This is a meter. It is approximately the length of a grown human's fingertip to chin, thereabouts. Okay. That's a meter. Is a nanometer bigger or smaller than a meter? Smaller. How much smaller?
9 minus 9. 9, 12, or 15.
If you divide a meter by 1,000, what do we make?
Millimeter?
We make millimeters. If we divide millimeters by 1,000,
Pico?
oh,
Oh no, Pico's way smaller. Nano then. No, wait, it's an ounce.
something before that. Micro is given symbol mu. It's the Greek symbol mu. It's like a U, only it has a flourish of a tail that comes into it. So think of a U and put a tail in it. So when you write it like that. It's a mu.
It is 10 in the
If you divide micrometers into 1,000 equal pieces, you get nanometers. Okay. All right. So, if I have a meter, I have 1 meter. If I divide it by 1,000, then I have 1 divided by 1,000 meters. Put that in your calculator. What is 1 divided by 1,000?
I should have that just,
0.001.
yeah, 0.001, that's right.
Okay. Don't start the word with the point.
Okay.
Include the 0. Yeah, must include the 0 that goes before the decimal place, because it is 1, 2, 3 zeros. If you include the 0 that goes before the decimal, then you know that it was divided by 10 3 separate times. Divided by 10, divided by 10, divided by 10, because 10 times 10 times 10 is 1,000. 10 times 10 is 100, times 10 is 1,000. Okay? So this, in scientific notation, is 1 times 10 to the negative 3 meters. 1 divided by 10, but the opposite way of doing it 3 times. So divide by 10 3 times. Okay? This 3 tells you that there are 3 zeros in your number, one of which is before the decimal. If you take 1 and you divide it by 1,000 and then divide it by 1,000 again, that's 1 divided by 1,000,000, which as a decimal is 0.000001 meters. In scientific notation, this has got 6 zeros in it, and my value is behind the decimal place, 10 to the negative 6. The nanometer is 1,000th of this millionth, so that's a billionth of a meter, which is 0.0000000001. And at this point, if you have to write that many zeros out, you're running the risk of doing it wrong. Here, scientific notation comes in and just says, you're less likely to do this wrong. Plus, your calculator might not have that number of digits on it. Some calculators only have 8 digits. That decimal number is not possible on many calculators. Okay? So, UVA, UVB, and UVC are these wavelengths. These are not frequencies, these are wavelengths. A wavelength is exactly what it says it is. It is the length of one wave. It's the distance. This is a meter. This is meter. On the other side, I think, is so a yard is here. This is a meter. Meter is this much longer than a yard. Okay. The whole thing is 1 meter long. these top little gradations are 1,000th of a meter. Those are millimeters. There's 1,000 of those little tiny lines in this. So that's 1 millimeter. Each one of those little tiny lines is 1 millimeter. Divide them by 1,000 again, you get micrometers. Divide them by 1,000 again, and you get nanometers. 200 of them is the wavelength of ultraviolet A, and then ultraviolet B, and then ultraviolet C. Of these three waves, which one's the highest energy? A, B, or C? Why is A the highest energy?
It's the electromagnetic spectrum when you're going across, it starts with UV at 400 or below.
Oh, so you actually know the numbers.
Well,
Okay.
yeah, but so it goes to the right, and that's where it goes high energy.
So these are the lengths of waves. 320 is longer than 200. So if this represents 200, then 320 no, it'd be bigger than that, wouldn't it? Yeah.
Why would it be longer if it's smaller?
It's a long. This is a longer wave, and longer waves have lower frequency. Frequency is tied to energy directly. Wavelength is tied to energy inversely. So this is the highest energy, and then this is the lowest energy, which, without knowing anything physiological about what's going on, which one's the most dangerous? Yeah, the highest energy wave. Okay? So we get uneven amounts of A and B and C, and one of our chemical agents is going to come to our salvation. Sunblock. Sunblock. Okay, our book actually talks about sunblock in section 1.5 and 1.6. Okay, let's actually have a read, see if there's numbers. The relative biological sensitivity per photon. Okay. A reduction in stratospheric ozone allows more UVB light to penetrate the Earth's surface. A 1% decrease in overall ozone results in a 2% increase in UVB at ground level. Okay, so you go to the beach, we do something on the planet that makes the ozone go away. If I had 100 molecules of ozone and I just get rid of one of them, so that's 1% decrease, I double the amount of ozone. No, 2% increase. No, not 1 to 2%, that would be a double. I increase the amount of ultraviolet by 2. Well, the effect is double, but they're not doubling the effect of ultraviolet. Okay. This increase in UVB is the principal environmental concern about ozone depletion because it leads to detrimental consequences to life forms, including humans. Exposure to UVB causes human skin to burn and tan at the beginning, and then cancer. Exposure to UVB causes human skin to sunburn and suntan. Overexposure can lead to skin cancer, the most prevalent form of cancer. The most prevalent form of cancer amongst all humans is skin cancer, not lung cancer, not colon cancer, not breast cancer, skin cancer. And by the sounds of that, an awful lot of it is avoidable. Avoidable. There are things that your doctor tells you about. You would radically increase your likelihood if you have a sunburn in your childhood.
Because you're exposed to it.
Yeah, yeah. If you were burnt in your childhood, which many of us were, then that's a risk factor. Doesn't mean you're going to get it. It's just a risk factor. It's just an increase. You know, they built Texas a mile and a half away from the sun. That doesn't help. If you live at northern latitudes, then you experience bad weather and grayness. And so you would think that, well, those people are less exposed to the sun, but those poor fools, the first day that it's sunny, they all go outside on purpose and expose themselves to the sunlight. Whereas people in the southern climes, we see the sun and we avoid the sun. Most of us. Most of us. When I lived in Michigan, it's quite north. It's cold it's desperately cold for months of the year, and lots of people tan. They go to tanning salons. This is a risk factor. This is an increased risk factor because the tan is like here. But you're exposing yourself to this. And even the brown people that I knew in Michigan, and Michigan has a very, very large Arabic community. They also tanned because it's fashionable. It doesn't seem right. Doesn't seem right. Massive risk factor.
So it's better to tan in the sun than may.
I think they actually have some studies on it that it's really bad. The tanning.
This is not medical advice. Yes. That is not medical advice. I am not board certified to tell you one way or the other, but intentional tanning is not a good idea. Not a good idea. Most biological effects of sunlight arise because of UVB. It is absorbed by a very important molecule called DNA. DNA is the repository of all of our genetic information, and ultraviolet breaks it. There's a little diagram about how so it's a kind of an awkward diagram. I mean, its scale is correct, but you're going to read the scale backwards because low numbers are the high energy events, which are the ones to be avoided. So if they'd have written this instead of wavelength, that had written it as frequency, it would be flipped the other way. Okay, so we've got wavelength here, and as that wavelength decreases, our waves get higher in energy, and the damage to DNA goes whoop, upwards. I would do this one. I would do that one backwards. The reason that they don't do it backwards and do frequencies is that wavelengths are easier to understand than frequency. Wavelengths are small, palatable numbers, even if we have to make them be in nanometers. Frequencies, The frequency of this wave is in hertz. We have no alternative other than hertz. I can't change the units to make my number be more palatable to the general public. So yeah, frequencies are harder to understand in terms of numerical values. That's why. Okay, most skin cancers in humans are developed by overexposure to UVB. So any decrease in ozone is expected to yield increases. Fortunately, the great majority of skin cancers are not fatal. Oh wow. Skin cancer has a 25% mortality rate. Okay, that sounds bad. That sounds bad, but 75% is survivable. There are cancers out there that have a 100% mortality rate. Yeah. Pancreatic cancer. Nobody has ever survived pancreatic cancer. That's one that we need to have a look at. The incidence of malignant melanoma is related to latitude. White males living in sunny climates like Florida or Texas, shout out, are twice as likely to die from the disease as those in the northerly states. Okay? We mostly actively avoid the sun in the summer. Do we actively avoid the sun in the winter when our winters are as warm and sunny as northern summers? Yeah.
And for whatever reason, the cooler it is, the less like inclined you are to actually put sunscreen on as well.
Yeah.
So
Yeah. Australian women have about twice the mortality rate as their counterparts in the United Kingdom or Canada. Though dramatic increases from the 1950s to the 1990s seem to have stopped or partially reversed, that's behavior, that's tanning culture, that's people. Once upon a time, if you wanted to show your affluence, you would be porcelain white. You would be pale. That meant you were so rich that you could stay indoors. That you did not have an outdoor job. You weren't involved in manual labor. And it was desirable to be pale. And then somewhere around the 1970s, vacation culture caught on, and people took vacations in hot, sunny places, and the way to demonstrate their wealth to the outside world is to come back with a suntan. And now people are orange. But, yeah, yeah. People, it's safe.
it's a choice.
Safer, we think, we hope. And then sunscreens. Sunscreens block ultraviolet. We have ultraviolet spectrophotometer in the lab, and there's a little lab experiment we could do. We could take 20 minutes out of a day, go to the lab, and smear some sunblock onto a cuvette, stick it in the ultraviolet, and see that the peak goes bloop, just disappears. And different sunblocks contain different agents, and they make different claims about which parts of the full UV spectrum that they're going to block. A&M has I think it's it's the second lab in their organic chemistry lab sequence. It's ultraviolet sunblocks. Yeah, we could do that. There's a couple of things in here. The white block that is paint, zinc oxide or titanium oxide. That's paint. the first people I ever saw with this, and I don't see very many Americans with it, Australians. They go to the beach and they think about where they're going to get burnt, and it's right here, and the part that points out and is prominent, and you just put like white paint on it, and it doesn't get burnt anymore. So they block massive amounts. Okay, so the term full spectrum is sometimes used to denote sunscreens that block UVA as well as UVB. The use of sunscreens that block UVB but not A may actually lead to an increase in skin cancer. Which one's the dangerous one?
B.
Yeah, well, this
A
is the
is
high
most
energy, but like this one is this big culprit right here. So if we only block that one but don't leave that one in, we can get like false sense of security. And I take away some of the symptoms, but I don't take away the exposure. Okay. Substances used in sunscreen that reflect or scatter light, the white paints like zinc oxide or titanium oxide, before it reaches the skin, those are blocks. Sunscreens, we're talking about nanoparticles, and then here's your sun protection factor, your SPF. What did we learn about SPF?
Go by factor, so 15 times longer you can stay in the sun than if you were without sunscreen.
Mm-hmm.
Now, how long you're supposed to stay in the sun without sunscreen?
And what number are we being advised to use?
30, right? I thought
Ooh.
30. Isn't 30 the general? Or
Isn't that low?
Well, they say the higher you go, it's not as effective because of, I think they didn't even give the efficacy of the sunscreen. It's because of your like mentality to it. You have a false sense of protection. The 60.
Okay. So they make 80s and 85s. Do they make 100?
Yeah,
I think
they
they make
do.
100. They
They
make 100.
Normal.
And if you have kids, the pediatric sunblock needs to be as high a number as you possibly can be. I think dermatologists want you to use the biggest number possible, and 30 would probably raise an eyebrow at your dermatologist. We are over time. I have kept you too long.
What kind of sunscreen I use?
Yeah.
It's at least 30,
Okay.
but they say 50 is the best.
Okay. And that means that you can stay in the sun 50 times longer than if you had no protection at all.
But what's the time with no protection?
Yeah, so that's what I don't understand. So I was trying to figure. So skin max time.
Is there any sunscreen that blocks all three at the same time?
Yeah, your zinc oxides,
Time of day
I think
depends,
it's a barrier,
with like the UV.
but you're not
index.
gonna want
Okay.
So
to
All three.
paint yourself.
if it's a UV index between 8 and 10, our summertime
We're
tell
higher.
you, we're higher. We're typically 10 to 12.
Yeah.
So 8 to 10 on my UV is 15 to 25 minutes, but under 10 minutes for if the UV index is 11 or higher.
Okay, so most
Yeah.
of the time it's
So like
Around 10
you
minutes.
go out of the house, you go to your
Yeah.
car,
Yeah.
and then you drive, you're fine, right?
Yeah.
But you're
Can it be
taking your
made?
dog for a
Oh,
30-minute
yeah.
walk.
Very, very easily, and we'll
Yeah.
talk
So
about,
that makes, so then it's 15
I think we'll
times
talk about that
so
too.
say 30.
Spark.
If it's
30
made,
SPF.
You can make it with ultraviolet light, you can make it with a spark.
you get like
300
Yeah.
minutes, so
sunscreens
yeah,
made out of
2.5
ozone?
Yeah,
hours, something like that, yeah.
and then block the UV.
So-
No,
Yeah.
when we find
It's like
ozone's
the
true
baseline.
nature, you're gonna want nothing to do with it.
Yeah.
I've never like thought about, I've
Okay.
thought about it, but.
Well, sorry for keeping you late, we'll see you next